Mammals regulate their daily rhythms using a centralized master clock, the suprachiasmatic nucleus. Birds operate on a highly decentralized, multi-oscillator network. The structural baseline of this system is an endogenous oscillation maintaining a period, represented by the mathematical variable tau, of approximately 24 hours. This chart is an actogram, the standard chronobiology tool for mapping these behavioral rhythms over time. Looking at the top, the alternating light and dark bars represent the environmental solar cycle. We call this the external phase, or phi-E. The dense black blocks plotted below represent the bird's actual locomotor activity. The exact onset of this daily activity is the internal phase, or phi-I. The alignment between that external solar cue and the internal activity onset is the phase relationship, psi-E. In an entrained bird, this alignment remains stable. To determine if this rhythm is generated from within, researchers place the bird in constant darkness. Uncoupled from external cues, the internal period drifts naturally, free-running slightly longer or shorter than a strict 24 hours. Isolating the organism in these constant conditions allows researchers to strip away direct environmental forcing and measure the raw biological clock. Introducing artificial light at night creates a disruptive variable to test that clock's integrity. These actograms show what happens when great tits are exposed to dim artificial light at night in the shaded middle section. Their activity onsets clearly shift earlier. The analytical challenge is determining whether this light permanently phase-shifted the endogenous clock or merely forced a temporary behavioral reaction. We find the answer by returning the birds to constant darkness at the bottom of the record. The activity onset immediately snaps back to perfectly align with its original trajectory from before the artificial light was introduced. This phenomenon is known as masking. The light altered the bird's physical behavior, but completely bypassed the central timing mechanism. Because environmental cues can mask behavior, identifying the actual pacemakers of the circadian system requires physically dismantling them. Mammals require intact retinas for light entrainment. However, if you surgically enucleate a sparrow, it still synchronizes to a light-dark cycle, proving birds rely on deep encephalic photoreceptors located directly inside the brain. For decades, the prime candidate for this master pacemaker was the avian pineal gland, sitting deep beneath the skull. This actogram tracks a house sparrow through a surgical pinealectomy, marked by the horizontal intervention line in the center of the data. In the 5 to 15 days following the surgery in constant darkness, the bird's consolidated activity fractures and decays into complete behavioral arrhythmicity. Yet, if returned to a 24-hour light cycle, these pinealectomized birds can still anticipate the time of lights on, indicating secondary timekeepers remain functional in the network. Even if it doesn't act alone, the pineal gland is an essential structural pillar. Without it, in the absence of light, the passerine circadian system collapses. To understand how the pineal gland enforces time across the organism, we must isolate its neurochemical output. This biochemical pathway illustrates the internal cellular clockworks of a pinealocyte. During the dark phase, the enzyme AANAT converts serotonin to NAS, driving the rhythmic synthesis and secretion of the hormone melatonin. Researchers tested whether this rhythmic melatonin actively sets the clock, or acts as a soporific to induce sleep, by injecting it into arrhythmic pinealectomized birds. These charts display the results of administering exogenous melatonin in continuous cycles of exactly 26 hours and 22 hours. The locomotor activity establishes a systematic, anticipatory phase relationship, locking into parallel alignment with the hormone schedule. This rhythmic synchronization confirms true entrainment. This autoradiograph maps exactly where that melatonin signal is received in the brain. The dense black areas in panel D reveal high-affinity melatonin binding, tightly localized in the visual suprachiasmatic nuclei, or VSCN. The pineal gland exerts its temporal authority by broadcasting a rhythmic melatonin signal directly to these receptors in the hypothalamus. This dynamic raises a mechanical question. If the pineal gland drives the rhythm, can it maintain that oscillation entirely on its own? To measure its native capacity without interference from the rest of the body, researchers isolated individual avian pineal glands in an in vitro laboratory culture. This plot captures melatonin secretion. Under standard light-dark conditions, the isolated gland produces robust, high-amplitude peaks synchronized to the dark phases. The true test of endogenous endurance comes in constant darkness. Over the next 72 hours, the amplitude of the melatonin peaks severely decays. The isolated pineal gland behaves as a damped oscillator, exhausting its rhythmic output in 2 to 8 days. This poses a biological paradox. If the primary pacemaker chemically decays in isolation, a free-living bird in constant darkness should rapidly lose its internal rhythm. The pineal gland must receive a sustaining input from elsewhere in the network. The VSCN acts as a secondary active pacemaker, firing precisely when pineal output goes dormant. The physical circuitry itself provides the clear evidence. The SCN drives a sympathetic postganglionic neural pathway that routes all the way back up into the pineal gland. During the bird's subjective daytime, an active SCN sends a signal up this neural fiber, releasing the neurotransmitter norepinephrine directly onto the pineal sites. When norepinephrine binds, it inhibits daytime melatonin synthesis, while simultaneously triggering a reset that boosts the amplitude of the underlying cellular clockworks. The VSCN acts as a daily chemical shock paddle, delivering an essential pulse of norepinephrine that prevents the pineal gland from giving in to its innate tendency to damp out. Combining these two halves gives us the unified theory of avian circadian organization, the neuroendocrine loop model. Looking at this anatomical diagram, we can trace the complete circuit. The night phase of the loop begins with the pineal gland synthesizing melatonin, sending a highly inhibitory signal down to the SCN. Because pineal is a damped oscillator, its melatonin output naturally diminishes as dawn approaches. This drop in melatonin chemically disinhibits the SCN, allowing it to become active. During the day phase, the active SCN routes a sympathetic signal back up to the pineal gland, delivering the norepinephrine that restores the pineal's amplitude for the following night. This dynamic equilibrium is called internal resonance. Two distinct damped pacemakers maintain perpetual rhythmicity by mutually inhibiting and resuscitating one another in an infinite anti-phase loop. The elegance of the avian clock lies in its decentralization. It eschews a dictatorial master clock in favor of a distributed, interdependent network operating in perfect biochemical tension.